first. There are two things that are left from that section. One is what is called the first derivative test. Derivative test. And another topic is known as the second derivative test. And so what are these tests about? These are about the following. So given a critical point of a function, determine whether you have a local maximum value or a local minimum value there. Remember, in section 3.1, we saw that local max and local mean values may only occur at the critical points, right? So these two tests are testing whether a given critical point, whether at a given critical point we have a local max or a local min. Okay, so these two tests, whether at a critical point we have a local max or a local min. Okay, and I'm going to explain how these two tests work through an example. So, and I'm going to use the same example that we used last time. Last time we looked at this function f of x, which is the following: 3x to the 4 minus 4x cubed minus 12x squared plus 5. And last time we calculated the derivative of this function, and the derivative, so let me write down the way that this question will be phrased. The question is the following: find the critical points of this function f and classify them. So when I say classify them, I mean at each critical point, do I have a local max or do I have a local mean? That's what you want to classify. Well, to answer this question, the very first thing that you have to do is you have to find the critical points, right? So how do you find the critical points? Well, you have to find the derivative. And the derivative in this case, remember, was 12x cubed minus 12x squared minus 24x. And then we factored it out as 12x times x, minus 2 times x plus 1, I think. So we factored it out in this way. And so the critical points are what? The critical points are 0, 2, and negative 1. And then we want to know, so there are 3 critical points, right? And remember, this derivative is defined everywhere. So there are no values of x where the derivative doesn't exist, right? In this case, So these are the only critical points. And is everybody okay? I don't have to solve where the derivative doesn't exist in this case, because the derivative is defined everywhere. Am I making sense? Okay, so these are the only critical points. So now, once I have these critical points, I'm actually going to do the same thing as I did before, which is come up with the sine graph for the derivative function. So remember, the sine graph for the derivative function was the following. This is the domain of the function. The domain is everything, right? The domain, this is a polynomial function, so the domain is everything. The critical points are -1, 0, and 2. And then what did we say about the sign of the derivative at each subinterval here? If you, yeah, I think the derivative to the left of -1 was negative, right? So this was negative here, and then it was positive here, and then it was negative again here, and then it was positive here, right? If you look into your notes, so that's what you're going to find. And then what can I say about the function f then? I can say that the function f is decreasing here, right? It is increasing here, and it is decreasing here. It is increasing here, right? From this picture, is it clear that at -1 I have a local what? Look, on the left side of -1, the graph is decreasing, right? On the right side of -1, the graph is increasing, right? So at -1, I have a local mean. So I have a local mean at -1. Local mean is equal to f of -1. And then at 0, what do I have? Local max. Because on the left side of 0, the graph is increasing. On the right side of 0, the function is decreasing. So I have a local max there. So f of 0 is a local max. And finally, at 2, I have a local mean. Is everybody okay with that? Is that okay? So this is actually the first derivative test. We actually used the first derivative test here. So what does it say? Well, it says that suppose you have a critical point, let's say -1. If on the left side of the critical point, the derivative is negative, and on the right side of the critical point, the derivative is positive, then at that critical point, I have a local mean. Look at this critical point. On the left, if on the left side of the critical point the derivative is positive, on the right side of the critical point the derivative is negative, then I have a local max there. That's what it says, okay? Which is exactly what we did last time, right? So this is nothing new. Just make this sine graph for the derivative. That tells you where the function is increasing and decreasing, and that tells you exactly where the local max is and where the local mean is. Is everybody okay with that? So if I say in the exam or in a quiz, use the first derivative test to identify the local maximum and the local minimum values of the function, what would you do? Exactly this. Nothing new. Am I making sense? Okay. So now we are going to look at the second derivative test for the same function. So again, I have the critical points of the function, right? And I want to know whether at each one I have a local max or a local mean. We already know that, but I want to do the same thing with the second derivative test. So before I go there, let me first say that the second derivative test does not work for the critical points where the derivative doesn't exist. So if you have a critical point where the derivative does not exist, then the second derivative test doesn't apply. The second derivative test will not tell you whether you have a local max or a local mean there. Am I making sense? If you have a critical point where the derivative does not exist, the second derivative test does not tell you whether you have a local max or a local mean there. However, if you have a critical point where the derivative is 0, which is the case here for the 3 critical points. So suppose C is a critical point of a function f, and the derivative at C is 0. So this is a critical point because the derivative is 0 there. It's not a critical point because the derivative doesn't exist there, okay? So in this case, we can use the second derivative to classify whether I have a local max or a local mean there. How? Well, first of all, we need an assumption in the second derivative test. So this is the second derivative test. And there is an assumption needed, that is f double prime is continuous near C. So what it means is that the second derivative function is continuous in an interval containing C. You don't have to worry about that all that much when you do the problems, but the second derivative needs to be continuous near C. But what does it say? Well, if the derivative at C is 0, how does the tangent line look like at C? How does the tangent line look like at C? You would agree that it's a horizontal line, right? The tangent line at C will be a horizontal line. Would you agree with that? The tangent line at C would be a horizontal line. So let's say this is the point C, where this is the point C, CF of C, okay, CF of C in the graph of the function, and I know that at that point the tangent line is horizontal. So the line is the tangent line at that point. Also, this is the point where I have the point C, F of C. And again, I'm drawing 3 different pictures here because there are 3 possibilities that happens. Now, suppose that I know that the second derivative at C is positive. So suppose that I know that the second derivative at C is positive. What does it tell me about the graph at C? Second derivative at C is positive means the function is concave up, which means the graph must look like this, in which case at C what do you have? Local mean, right? On the other hand, if you know that the second derivative at C is negative, now the graph would be concave down near C, in which case you have what? Local max. But there is another possibility. The other possibility is that the graph looks like something like this. Okay? So at C, the tangent line is horizontal, but you have neither a local max nor a local mean at C. So in the third picture, you have neither a local max nor a local mean at C. Am I making sense? So in this case, there is a third case where the second derivative at C may be 0. So if the second derivative at C is 0, then it may be the case that you have neither a local max nor a local mean there. However, it's not always true. So if the second derivative at C is 0, then the second derivative test is inconclusive. Inconclusive. What does it mean? It means that the second derivative test will not tell you anything whether you have a local max or a local mean there. So what I'm saying is that just because the second derivative at c is 0 doesn't necessarily mean that you have neither a local max nor a local mean. Oftentimes it is, but there are examples where even after this you might have a local max or a local mean there. Am I making sense? But the second derivative test will not apply. If the second derivative at c is 0, it doesn't tell you anything. So which test is better? Well, it's hard to say, but the first derivative test always applies. Okay, it's going to tell you what are the local max and local means if you can carry out the computations. But the second derivative test has some shortcomings. Like this, if the second derivative at c is 0, then you don't know whether you have a local max or a local mean there. Am I making sense? So why use the second derivative test? Well, I mean, there are some applications where it is easy to carry out. Okay. So in any case, so how do I apply the second derivative test in the problem that we just did? So remember, in our problem above, we had the function f of x, which was what? 3x to the 4 minus 4x cubed minus 12x squared plus 5. This was the function that we had, and we computed the first derivative, and we found that the first derivative was 12x cubed minus 12x squared minus 24x. And then we also found the critical points to be what? 0, -1, and 2. These are the points where the derivative is 0, right? These are solutions. These are solutions of the equation derivative equal to 0, right? Remember that. So these are the critical points of f. And what's the second derivative in this case? The second derivative is given by 36x squared minus 24x minus 24, right? So that's the second derivative. So how do I decide whether I have a local max or a local mean at each of these critical points? Well, very simple. You evaluate the second derivative at each of the critical points, okay? So you calculate f double prime of 0, f double prime of -1, f double prime of 2. What is f double prime of 0? -24, so that means it's negative, right? And that implies f of 0 is what? If at 0 the second derivative is negative, it means that the function is concave down, so I have a local mean. At -1, if I plug in -1, what do I get? What's that? If I plug in -1, then yes, it's positive, which implies that f of -1. Well, if f of -1 is positive, it means that at that point the graph is concave up, and so I have a local max there. Local max.
Vice versa.
Yeah, I think I made a mistake, didn't I? Yes. I have to switch them. So I take back what I said. This should be a max here, this should be a min. Again, if the second derivative at 0 is negative, it means that the function is concave down, and if the concave down, I have a local max. And if it is concave, in the second case, it is concave up, so I have a local mean if it is concave up. And in the third case, I think f double prime of 2 is also positive, right? Because if you plug in 2 here, you get 36 times 4 minus 24 times 2 minus 24. And I think it's pretty clear that it's positive. And this is, you can also use your calculator to see what that is. So f of 2 then is a what? Local minimum. Because if the second derivative is positive, means the function is concave up, meaning that at that critical point you have a local mean. Is that making sense? Is everybody okay with that? So let me go up. So last time, remember, for this function, we came up with where the function is increasing and decreasing, where the function is concave up and down, right? But I think I didn't give you the graph of that function. So let me complete the discussion on this function by giving you the graph of that. So let me draw the graph of this function. So let's say I have the x-axis here. I have the y-axis here. Okay, how would I draw this graph? What are the what are the critical points? Remember, we looked at the same function. I'm talking about the same function that we just discussed about. For that function, I found the critical points to be 0, 1, and what? 0, -1, and 2. Now, did we also find out the points where the concavity changes? We also found out the points where the second derivative is 0, right? Okay, what did we find? We found, let's say, -1. Let's say -1 is right here, okay? And this is where 0 is. I think...
You're not meant to teach anymore.
Okay, so I think the second derivative was vanishing at 1 minus √7/3, was it? And 1 plus √7/3. We can check. Right here. The second derivative was the critical points for the second derivative we found was 1 minus √7/3, 1 plus √7/3, and I think these are about 0.54. Okay, and this is about negative 0.54, I think. If you have a calculator, could you check that? So negative 0.54, that number would be somewhere here. 1 minus √7/3. And then, of course, 1 would be here, and 2 would be somewhere here. And right here would be 1 plus √7/3. So once I have these 5 critical points, I'm going to plot the points corresponding to these numbers, these x values. So what's the value of the function at -1? The original function. The value of the function at -1 is 0, so I get the point 0. What's the value of the function at 0? Let's say 1 is up here. The value is 5. Okay, so I'll just have a bad scale here. So this is, let's say, 5. So this is the point 0.5. This is the point -1, 0. At 2, the value of the function is in fact -27. Again, I will have to allow some bad scaling here. This is 2 and -27, I think. And the value of the function at 1 minus root 7 over 3 and 1 plus root 7 over 3, whatever they are, they are positive values, okay? So, and I think they have the equal values there, okay? So now we have to draw the graph. What is happening on the left side of negative 1? On the left side of negative 1, if you look at the increasing decreasing behavior, the function is doing what? The function is decreasing on the left side of negative 1, right? If you look at the sine graph, right here, the function is decreasing up to negative 1, increases up to 0, decreases up to 2, and then increases again. So I know on the left side of negative 1, the function is decreasing. Now it is decreasing from where? Decreasing from infinity, right? Remember, as x goes to negative infinity, the value of the function goes to infinity. We saw that last time. So I know that the graph is coming down from infinity like this, and it is concave up until negative 1, right? You guys are okay with that? And then it is also concave up to up until 1 minus root 7 over 3, and after negative 1 it's increasing, right? After negative 1 it's increasing and concave up until 1 minus root 7 over 3. Now between 1 minus root 7 over 2 and 3 and 1 plus root 7 over 3, the function is concave down, but up until 0 it's increasing, right? So it is concave down now. It is concave down up until this point, and it is increasing up till 0 and then decreasing. Now from that point up until 2, what is happening? Decreasing still, and now it is concave what? Concave up. So from that point, you have to forgive my drawing here. So this is concave up here, and then after 2, the function increases to infinity, right? Increases to infinity, and it's still concave up. So it goes like this. Is that making sense? So you have to match what you have found. The function, remember, was decreasing up until negative 1, increasing up to 0, and then decreasing up to 2, and increasing again. That's what we found. And also we found that the function is concave up until 1 minus root 7 over 3, concave down until 1 plus root 7 over 3, and then concave up again. Okay, if you look at what we found, that's exactly what we found. And do I indeed have a local max at 0? I have a local max at 0. I have a local mean at negative 1. I have a local mean at 2 as well. Is everybody okay with that? You guys are okay with that? Any questions? Any questions at all? Anyone? No? Okay. We are done with section 3.3. As I said, we finished 3.4 long time ago. So now we look into section 3.5. Now, section 3.5 doesn't have any theories. That is, we are done with everything that we learned in 3.1, 3.2, mainly 3.1 and 3.3. We are going to apply that in 3.5. So what is 3.5? 3.5 is about sketching graphs of functions. So 3.5 is about steps that goes into sketching the graph of the function. So how do you sketch the graph of a function? Okay, what steps do you follow? That's what we are going to do. Well, you already have an idea, right? We came up with this graph, and what did we follow? We followed some steps to come up with this graph. So what are the steps that we followed? Number 1, we need to know the domain. Number 2, we needed to know the terminal behavior. What happens when x is big? what happens when x is large and negative? We saw that when x is large and negative, the function is large. When x is large and positive, the function is large as well. So that's how we know the terminal behavior. Then we came up with where the function is increasing and decreasing, where the function is concave up and down, and then we sketch the graph of the function. Is everybody okay? So, if you have a, in real life, none of you will probably, draw the graph of a function by hand. Okay, you will basically use a computer algebra system. You'll say, here is the function, show me the graph, and it's just going to show you the graph. Okay, so what's the point of learning how to sketch the graph of a function? Well, first of all, you need to understand the steps that goes into sketching the graph of a function. That doesn't mean you're going to use that. You're going to do that by hand to come up with the graph, but it tells you a lot about the function. So if you understand how this works, you understand all the concepts that we have gone over so far. In fact, in the entire course, everything really comes down. This is a melting point because in the next exam, I can really ask you just one question. The one question would be sketch the graph of a given function, because it takes into account concepts from 3.1. It takes into account all the concepts from 3.3. So I can just ask one question and I'll be done with that. Okay, yeah.
Does that mean exam is just one question?
Now, well, it's a one question, but there are so many steps here, right? There is a step where you have to find the increasing, decreasing, and so on, concavity. So why do I? Well, I won't be mean and ask you just one question, okay? And the reason it will be mean is that when you find the derivative, right, you have to simplify that. You have to find the critical points. If you make one error there in the derivative simplification, you'll be wrong with the second derivative, and then you just be entirely wrong, okay? And you basically lose the entire grade, right? So what I'm going to do is make a separate question. Like I said, find where the function is increasing and decreasing for one function. For another function, find the concavity, and then there will be other problems. And one last problem would be that I will give you most of the information that you need to come up with the graph. No, I said there will be others, and then the last one. But I haven't said what are the other. I haven't said anything about 3.2. Okay, so we have 3.2, 3.7, 3.9 that we haven't really talked about. Well, we finished 3.2, but we haven't talked about 3.7 yet. Okay, so without any more time, let me do an example from section 3.5. Now, the video that I sent you yesterday, that video, the first part of the video is on section 3.5. I carry out how to sketch the graph of a function in that first part of the video. Okay, so I have an example from 3.5 in that video, and I hope that you'll watch it, and that's going to be that's going to help you to do all your homeworks from section 3.5. What I want to do here is that I'm going to do another example. Okay, different than the one that you'll see in the video. And that example is the following. So we are in section 3.5. So maybe I'll write that here, section 3.5. And we are going to sketch the graph of the following function. The function is f of x. It is x times root of 6 minus x. That's the function that we want to sketch. Is everybody okay with that? Okay. Step number 1. What do you think the step number 1 is? Find the domain of the function. How do I find the domain? In this case, the only restriction is that I need the quantity inside. The function is defined as long as 6 minus x is what? As long as 6 minus x is non-negative, the function is defined, right? So which means 6 is larger than x, and then x is less than or equal to 6. So what's the domain? The domain of the function f is then negative infinity up to what? 6, and I have to include 6, right? You guys are okay with that? So that's the domain. That's the first part. All right. Once we have the domain, the second step. The second step is you want to determine the terminal behavior. Terminal behavior. And here you will also know whether you have any horizontal asymptotes or vertical asymptotes. So any horizontal asymptotes or vertical asymptotes. So do I have any horizontal or vertical asymptotes? We'll also know that in this step. So what do I do? Well, note that the domain is from negative infinity to 6, right? So I need to know how the function behaves near 6 and how the function behaves at negative infinity. Okay? So notice that the function is defined at 6, and would you say that the function is continuous at 6 from the left? Okay, what's the limit as x goes to 6? Remember, the function is undefined on the right side of 6. So as x goes to 6 from the left side of 6, what can I say about the value of the function? It is limit of x times 6 root of 6 minus x. X goes to 6. And that's exactly the same as 0, right? Which is the same as the value of the function at 0. Okay? And now I need to know what's the behavior of the function at negative infinity. So what's the limit as x goes to negative infinity of the function x root of 6 minus x? What would you say? As x goes to negative infinity, what can you say about x? X goes to negative infinity, and what can you say about the second factor? It goes to positive infinity. As x goes to negative infinity, negative x goes to positive infinity. So 6 minus x will go to positive infinity. So this is going to positive infinity. So one factor is becoming large negative, the other factor is becoming large positive. Product will be large negative, right? So the limit is negative infinity, okay? Is everybody okay with that? So that's the terminal behavior. Do I have any asymptote? No. If the limit at negative infinity was a number, then I will have a horizontal asymptote. If this limit at 6 was infinity or negative infinity, then I will have a vertical asymptote. But I have none. So no. So in this case we have no horizontal asymptotes, no vertical asymptotes. Okay? Okay, so that's step 2. What is step 3? Step 3 would be intercepts. Intercepts, if you can find them. Sometimes finding the intercepts could be complicated. So intercepts. So what are the intercepts? Well, what is the x-intercept? How do I find the x-intercepts? Yes, set y to 0. Remember, y is what? Y is the function f of x. And that is x times root of 6 minus x. And if you set y to 0, then we have x times root of 6 minus x is 0, and that's going to tell us x is what? 0 or 6. So these are so what are the x-intercepts? The x-intercepts are x is 0, y is 0, or x is 6, y is 0, right? These are the x-intercepts. What is the y-intercept? How do I find the y-intercept? Very good. So I have set x to 0, and then y is equal to x times root of 6 minus x. That will also be what? So the only y-intercept is 0, 0. Okay, so that's how we can find the intercepts. To find the x-intercepts, set y to 0 and solve for x. To find the y-intercepts, set x to 0 and solve for y. What is y? Y is equal to the function. Y is equal to the function. Is everybody okay with that? Everybody's okay? All right. Did I go over time last time? Okay. I'm going to end here. No, I'm going to end here because the next thing that I have to do is find where the function is increasing and decreasing, and that's going to take a lot of time. So tomorrow I'll finish this example, okay?